simplest method in linear programming. How we know? In linear programming, we have two different methods, the graphical and simplest method. The graphical is limited in solving linear programming problems having one or two decision variables. On the other hand, simplest method doesn't have this problem. Simple method is an approach to solving linear programming models, in which a series of repetitive operations are used to reach the optimal solution, and this procedure has a number of steps to find out a solution of the problem, and there may be any number of variables and constraints in the problem. And in this method, we have two different forms, the algebraic form and its representation, and the tabular form and its representation.
Solution to an LP could be restricted to just the finite set of extreme points of the visible region. To do this, we need to have an algebraic characterization of extreme points. First, we consider a fixed format to LP now as the standard form. Next, we consider an algebraic construction to obtain a specific type of feasible solution and show that such solution corresponds to extreme point of the feasible region. An LP in standard form has only equality constraints and non-negative variables. The objective function and constraint are simplified so that each variable appears only once. Any constant term in the objective function is not considered, and the constraint system is a system of linear equations where all variables appear on the left and constraints appear on the right-hand side. An LP in any form can always be converted to the standard form by including additional non-negative variables. For every less than constraint, add a slack variable to the left-hand side and transform the constraint to equal form. The slack variable is non-negative and has a zero cost coefficient. For every more than constraint, subtract a slack variable from the left-hand side and transform the constraint to equal form.
Hello, my name is Guillermo Eloceguis Morquecho, and I'm gonna talk of the simplex tabular method from the subject Operation Research. The simplex method as part of the linear programming is a method analytical capable of solving those models that become complex in the use of the graphical method by the numbers of variables used. Developed in 1947 by George B. Dantzig, the simplex method has become the general method for solving programming problems. Linear, unlike the graphical method, can be used when the variables of the problem are more than two, characterized by seeking better solutions than the graphical method to optimize the function objective of the problem. Basis of the simplex method. Before developing the method, some specifications will have to be made. Formulation of the model using a mathematical model for problem solving is the basis of linear programming. Remembering which models refers to the simplified representation of reality. Mathematical models in specific make it is important to point out issues for the modeler to consider. The simpler the model, the better the result. A model complex will not always be the best solution. The model must be validated before being implemented to know if it represents the real situation, and if not, it will be necessary to do corresponding settings. If things are done in a hurry, the model will go wrong, and meticulous analysis of the information collected must be made to identify what will actually be useful for the model. Models are one more tool for the decision maker.
My name is Cristopher Ríos Ramírez, and I will explain the slack, surplus, and artificial variables. A linear programming model has to be extended to comply with the requirements of the simplex procedure. That is, all equations must be equalities. Linear variables must be present in all equations. In the case of less than or equal to constraints, slack variables are added to the actual variables to make the equation an equality. In the case of greater than or equal to constraints, surplus variables are used to make the equation an equality. A surplus variable is the difference between the total value of the true variables and the number on the right-hand side of this equation. Thus, a surplus variable will always have a negative value. In any maximization problems, our tableau must satisfy the following requirements. All the slack variables, and thus surplus variables as well, must form part of the initial solution remix. The table must contain as many rows as there are constraints. The elements of the columns of variables appearing in the basis must form a unit vector. Artificial variables. An LP problem is solved by adding an artificial variable to the equation, that is, a variable that has a positive value. Just remember that an artificial variable has no significance pertaining on the solution of the problem. It is merely used to find a solution mix of the first simplex tableau. Although artificial variables will always form part of the initial solution mix, the objective is to remove them as soon as possible by means of the simplex procedure. As long as an artificial variable still appears in the solution mix, the final solution has not yet been found. As any other variable, artificial variables are included in the objective function, but the value attached to them creates another problem. In minimization problems, since the objective is to find the lowest cost possible, a very large value is allocated to the artificial variables.
Next, I will show how we can solve linear programming problems using simulators. In this case, we will be using the PHP simulator. This simulator allows us to solve problems using the graphical method and the simplex method. To show how it works, I show you a problem in which we have already identified our decision variables, the objective function, and the constraints. Now, in the simulator, we will select simplex method. For this case, we will put that it has two decision variables and two restrictions. We give in continue. We select whether the objective is to maximize or minimize. We fill in the fields of the objective function and the restrictions, and we continue. The simulator will add the slack variables. We give again to continue. It will show us the first table. We click on continue as many times as necessary.
I'm going to show you how to use the solver tool in Excel in order to resolve this linear programming problem that we have here. So I have prepared this little template, and the first thing that we can notice is a group of cells, and specifically these two ones in this row, where we're going to have to type in the numbers that corresponds to the x1 variable and the x2 variables in our formula. So in this example, we have 10 for x1 and 8 for x2. So I'm going to do that. Now in this cell called objective function, that's what the OF stands for. It's going to have the formula that basically is going to solve the Z equation right here. So in order to do that, we're going to have to do a sum product. So I'm gonna type it of the result of the problem that multiplies these numbers that we have typed here. So at this moment it's not doing anything because in these cells it has no value at all. So that's why it's showing a 0, but that's gonna be fixed in a moment. So here we can pass to the restrictions. We have 3 restrictions here, 3 restrictions in our problem, and then we're going to do the same. We're going to have to identify the values of the x1 variable and the x2 variable in each one. So I'm going to do that real quick. For example, in the x1, for all 3 of them, we have a 3, a 2, and a 4. So I'm going to type them. So 3, 2, and 4. And for the x2 variable, we have 20, 2, and 6. So 20, 2, and 6. So we're going to have this one in blank, just for a moment. And to the symbol, we're going to have to type the symbol that we are seeing in the restriction. That's only to a guideline for forward in the process. So in all 3 of them, we have less equal than. So we type it all 3 like this. And in the right side of the symbol, we're going to type the number that is in the right side of the symbol in our problem's restrictions. So we have 120, we have 9, and we have 24. So all done this, the only thing that we have left is a left column. I'm sorry. So we're gonna do the exact same as we did in the OF cell. We're gonna have to do a sum product of this row and the respective row that it has, that each restriction has. So for this one, we're going to have a sum product of these 2 pair of cells, but this time I'm gonna lock them by pressing F4, and then the restriction 1 group of cells. So we did that, and making it 0, and then we just drag it like this, and the formula is copied to all 3 of them. So we have prepared everything that we need to solve our problem. So now we're going to have to go to the data tab. We're going to look for the solver tool. So we click on it, and it is going to ask us for the objective function. So we're going to select the OF one that we have prepared here, and then we have to maximize it because in our problem it specifies to us we have to find a maximization of the formula. So we'll let it as it is, and then by changing the variable cells, we are going to have to choose the variable cells that we're looking for, which is x1 and x2. So now that we have that, we have to input our constraints or the restrictions. So we click on that, and a little dialog test is going to appear. So in the cell reference, we're going to put the left side of the restriction. The symbol is the same one that we have here. So we left it as it is. And in the constraint, we're going to put the right side of the restriction. So click on that, and it saves. So I'm going to do the same for 3 of them. Like this, and the third one. So now that we have elected, we click on cancel, and then in this drop menu, we're gonna have to choose the simplex linear programming because that's what we are going to resolve, and then we click on solve. We click on OK, and as we can see here, we have for the x variable we're going to have for that 5, and as a result of that, our formula is going to have a total of 45, and that's it.